Welcome back to my class in Integral Calculus. For today, we will take up another integration technique called Trigonometric Substitution. This integration technique will also be used when we go to the next integration technique known as integration by partial fraction. In particular, integration by trigonometric substitution will be used for integration by partial fraction for cases 3 and 4, where you have a quadratic factor for the denominator of a rational expression in the given integrand, and in case 4 you have a quadratic factor that is repeated. And in these cases 3 and 4 of integration by partial fraction, we will use integration by trigonometric substitution. Which trigonometric substitution you will use, it depends on the given, on the expression that you see in the given integrand. And these are the only three things that you have to remember for you to determine which trigonometric substitution you will use. If you see this expression, the square root of a squared minus x squared in the given integrand, then the trigonometric substitution you will use is x equals a times sine theta. If you see this expression in the given integrand, that means you have to use a trigonometric substitution, and in particular you will let x equals a times tangent theta. If you have this expression is square root of the square of a constant plus x squared, you will let x equals a times tangent theta. If you see this expression in the given integrand, the square root of the square of a constant minus x squared, the trigonometric substitution you will use is x equals a times sine theta. And finally, if you see this expression in the given integrand, the square root of x squared minus the square of a constant, you let x be equal to a times secant theta. We now take some examples. Consider number 1, we have the integral of dx over the square root of 16 minus x squared. 16 is equal to the square of the constant 4. And this expression in the given integrand, in particular in the denominator of the integrand, the square root of 16 minus x squared is of this form, is square root of the square of a constant minus x squared. And because we are given this expression, we make use of trigonometric substitution. In particular, we let x equals a sine theta. And for this example, the constant a is 4. 16 is the square of 4. Therefore, a is equal to 4. And we let x equals 4 times sine theta. Now, differentiating both sides, derivative of x is 1 multiplied by dx. And derivative of the right hand side is equal to 4 times derivative of sine theta, which is cosine theta. multiplied by derivative of theta, 1 multiplied by d theta. And in the given integral, we replace dx with 4 cosine theta, d theta. And we replace x with 4 sine theta, and we simplify the given integral. Integral of dx is now equal to the integral of dx 4 cosine theta d theta divided by square root of 16 minus the square root of x, and x is 4 sine theta. And you square it. And we simplify. We get the integral of 4 cosine theta d theta divided by the square root of 16 minus the square of 4 sine theta. By property of exponent, the square of 4 sine theta is equal to the square of 4 times the square of sine theta. And the square of 4 is 16 times the square of sine theta, sine squared theta. And you can see that we have a common factor in the denominator, 16. We factor out 16. And we get the integral of 4 cosine theta d theta and we factor out 16. The common factor is 16. And the other factor we obtain by dividing each of these terms by 16. 16 divided by 16 is 1. Minus 16 sine squared theta divided by 16 is sine squared theta. And to simplify further, we make use of trigonometric identity, in particular, one of the Pythagorean identities that says sine squared theta plus cosine squared theta is equal to 1. And from this equation, if we transpose sine squared theta to the right hand side, we get cosine squared theta is equal to 1 minus sine squared theta. Thus, in the denominator, we replace 1 minus sine squared theta by cosine squared theta. And we have integral of 4 cosine theta d theta over square root of 16 multiplied by 1 minus sine squared theta, which is equal to cosine squared theta. Hence, this becomes 16 multiplied by cosine squared theta. And this is equal to the integral of 4 cosine theta d theta in the denominator, we can get the square root of 16 and the square root of cosine squared theta. Square root of 16 is 4. Square root of cosine squared theta is cosine theta. Therefore, the square root of 16 times cosine squared theta is 4 times cosine theta. And you can see that cosine theta, 4 cosine theta over 4 cosine theta is 1. So this simplifies to the integral of d theta. And the integral of d theta is theta plus c, the constant of integration. And we have to write the answer in terms of the original given variable x. Again, we go back to our substitution. The substitution we use, x equals 4 sine theta. Dividing both sides by 4, we get sine theta is equal to x divided by 4. And from this equation, you can see that theta is equal to sine inverse sine of x over 4, or shift sine of x over 4. Therefore, our answer theta is equal to shift sine or inverse sine of x over 4 plus c. And the integral of dx over the square root of 16 minus x squared is equal to shift sine of x over 4 plus c. For second example, consider the following integral. We have the integral of dx over square root of x squared plus 81. You can see that in the integral we have the square root of x squared plus 81, which is similar to the expression the square root of a squared plus x. And if you have this expression, the square root of a squared plus x squared, we make use of the substitution, trigonometric substitution, by letting x equals a times tangent theta. Again, in the given integral, we have the square root of x squared plus 81, which is similar to this expression, the square root of a squared, the square root of the square of a constant plus x squared, except that in the given, we have first the square of the variable plus the square of the constant. 81 can be written as the square of 9. And if we have this expression in the given integral, we know that we have to integrate the given integral by trigonometric substitution. And we use this trigonometric substitution by letting x equals a times tangent theta. And for this particular example, we let x equals 9. 81 is equal to the square of 9. So we let x equals 9 times tangent theta. Next, we differentiate both sides. Derivative of x with respect to x is 1, multiply 1 by dx. And derivative of the right hand side is equal to 9 times derivative of tangent with respect to theta. And derivative of tangent from your calculus 1 is equal to secant squared theta. Again, derivative of 9 theta is equal to 9 times derivative of tangent theta, which is secant squared theta, times derivative of theta is 1, multiplied by d theta, We substitute in the given integral, we replace dx with 9 secant squared theta, d theta. And in the denominator, we replace x with 9 tangent theta, and we simplify. So the given integral is now equal to the integral of dx 9 second squared theta d theta. Divide by the square root of x squared. X is 9 tangent theta, and we square it. Plus 81. And we simplify the denominator. We take the square of 9 tangent theta. And this is now equal to the integral of 9 secant squared theta d theta. Divide by the square root of the square of 9 tangent theta by property of exponent is equal to the square of 9 times the square of tangent theta. The square of 9 is 81, multiplied by the square of tangent theta, tangent squared theta. Hence, the square of 9 tangent theta is 81 tangent squared theta. And now you can see that we have a common factor in the denominator, which is 81. We factor out 81 and we will make use of another trigonometric identity, in particular one of the 3 Pythagorean identities. So this is now equal to the integral of 9 secant squared theta d theta. And divide by square root of, we factor out 81. Common factor is 81, and we find the other factor by dividing each of these terms by 81. 81 tangent squared theta divided by 81 is tangent squared theta. Plus 81 divided by 81 is 1. And from your trigonometry, one of the 3 Pythagorean theorems says that the square of tangent theta plus 1 is equal to secant squared theta. In the denominator, we replace tangent squared theta plus 1 with secant squared theta. And so this expression now is equal to the integral of 9 secant squared theta d theta. Divide by the square root of 81. Tangent squared theta plus 1 is equal to secant squared theta. And this becomes square root of 81 multiplied by secant squared theta. But we can get the root of 81 as secant squared theta. The square root of 81 is 9. The square root of secant theta, square root of secant squared theta is secant theta. And this expression now, this integral is now equal to the integral of 9 secant squared theta d theta. Divide by the square root of 81 times secant squared theta, which is equal to 9 times secant theta. And you can see that 9 over 9 will cancel out because it's 1. And secant squared theta divided by secant squared theta is secant theta. So this expression simplifies to the integral of secant theta d theta. Or we cancel out 9 in the numerator and 9 in the denominator. We cancel out secant theta in the denominator and 1 secant theta in the numerator. And this expression simplifies to integral of secant theta plus d theta. And from our lesson from one of the integration rules in our lessons before, the integral of secant theta is equal to ln of secant theta plus tangent theta plus the constant of integration c. Again, the integral of secant theta is equal to ln of secant theta plus tangent theta plus the constant of integration c. And we have to write the answer in terms of the original variable x. And we need the value of tangent theta, which we can get from the substitution we used. X equals 9 tangent theta. Therefore, tangent theta is equal to x divided by 9. Divide both sides of this equation by 9. And we get tangent theta is equal to x over 9. Now we have to get the value of secant theta, and secant theta is the reciprocal of cosine. So we get first the value of cosine theta. By definition of the tangent of theta, tangent theta is equal to the ratio of the opposite over the adjacent. X is the opposite, the side opposite in the right triangle. X is the side opposite the acute angle theta. Therefore, in the right triangle, we write x in the side opposite the angle theta. And the adjacent side, the side adjacent to theta, adjacent is equal to 9. And this is the side adjacent to theta, the side of the right triangle that makes the acute angle theta with the hypotenuse, which is the side opposite the right angle. And cosine theta is defined as the ratio of the adjacent to the hypotenuse. And we have the adjacent side. The adjacent is 9. And we need to get the hypotenuse, which is this side opposite the right angle. And we can get the length of this hypotenuse by Pythagorean Theorem that says the square of the hypotenuse, which we denote by h squared, is equal to the sum of the squares of the legs of the right triangle. Or the square of the hypotenuse h squared is equal to the sum of the squares of the two other sides. The square of x and the square of 9, which is 81. And from this equation, we get h is equal to the square root of x squared plus 81, the square of 9. So cosine theta now is equal to 9 divided by the hypotenuse, and the hypotenuse is given by h. square root of x squared plus 81. But what we want in the final answer is the secant of theta. And to get the secant of theta, we simply take the reciprocal of cosine theta. The reciprocal of cosine theta is equal to secant theta. Cosine theta is equal to 9 over square root of x squared plus 81. And the reciprocal of 9 over square root of x squared plus 81 is equal to square root of x squared plus 81 over 9. And that is the value of secant theta. The square root of x squared plus 81 divided by 9. Now, our final answer is equal to ln of secant theta. Secant theta is square root of x squared plus 81 over 9. Plus tangent theta. Tangent theta is equal to x over 9. Plus C, the constant of integration. Therefore, the integral of dx over square root of x squared plus 81 is equal to ln of square root of x squared plus 81 over 9 plus x over 9 plus c, the constant of integration. For our next example, consider the following integral. We have the integral of dx over the square root of x squared minus 49. And you can see that in the given integral, the square root of x squared minus 49 is similar to the expression square root of x squared minus a squared, for which we will use a trigonometric substitution by letting x equals a multiplied by secant theta. Again, if we have this expression in the given integral, we are sure that we have to integrate the given integral by integration by trigonometric substitution by letting x equals a secant theta, where a is the constant here. And in the given example, the constant a is equal to 7 because 49 is equal to the square of 7. Hence, to integrate the given integral by trigonometric substitution, we let x equal 7 multiplied by secant theta. And differentiating both sides, derivative of x is 1 multiplied by dx is dx. And derivative of 7 secant theta is equal to 7 times derivative of secant theta. And from your differential calculus class, the derivative of secant theta is equal to secant theta tangent theta. Derivative of secant theta is secant theta times tangent theta and multiplied by derivative of theta 1 multiplied by d theta. And in the given integral, we replace dx with 7 secant theta tangent theta d theta, and in the denominator, we replace x with 7 secant theta, and we simplify. Hence, the given integral is now equal to the integral of dx 7 secant theta tangent theta d theta over the square root of x squared, but x is 7 secant theta, we square it. Minus 49. And this is equal now to the integral of 7 secant theta tangent theta d theta over the square root of the square of 7 secant theta by property of exponent in your algebra class. The square of 7 secant theta is equal to the square of 7 multiplied by the square of secant theta. And we get 49 secant squared theta. Minus 49. And now we have a common factor 49 in the denominator. In the radical, we factor out 49. And this expression is equal to the integral of 7 secant theta tangent theta d theta. We factor out 49 and we find the other factor by dividing each of these terms by the common factor 49. 49 secant squared theta divided by 49 is secant squared theta. Minus 49 divided by 49 is 1. Hence the other factor is secant squared theta minus 1. And in the denominator, we make use of another trigonometric identity. In particular, we make use of one of the 3 Pythagorean identities to simplify secant squared theta minus 1. One of the 3 Pythagorean identities says that the square of tangent plus 1 is equal to secant squared theta. And we transpose 1 to the right hand side. And we would get secant squared theta minus 1 is equal to tangent squared theta. Again, we transpose 1 to the right hand side. We take the opposite sign of positive. And we get secant squared theta minus 1. And at the left hand side, we have tangent squared theta. In this expression now, we replace secant squared theta minus 1 with tangent squared theta. And this expression becomes the integral of 7 secant theta tangent theta d theta over square root of 49 multiplied by tangent squared theta. But we can get the square root of 49 and tangent squared theta. The square root of 49 tangent squared theta is equal to 7 multiplied by tangent theta. And this expression simplifies to the integral of 7 secant theta tangent theta d theta divided by 7 tangent theta. And you can see that we can cancel out 7 over 7, which is 1. And we can cancel out tangent over tangent, which is 1. And we are left with the integral of secant theta d theta. And again, the integral of secant theta from one of the integration rules we had taken before. The integral of secant theta is with respect to theta is equal to ln of secant theta plus tangent theta. Plus the constant of integration c. Now we have to write this in terms of the original variable x. We already have the value of secant theta from this substitution that we use, x equals 7 secant theta. And we divide both sides by 7, therefore secant theta is equal to x divided by 7. And secant theta is the reciprocal of cosine theta, and cosine theta is equal to adjacent over hypotenuse. And the reciprocal of adjacent over hypotenuse is hypotenuse over adjacent, which is equal to secant theta. Therefore, x over 7 is the ratio of hypotenuse over adjacent. And now we will find the value of tangent theta in terms of x. And to find the opposite side, we construct the right triangle with hypotenuse equal to x and the side adjacent to theta equal to 7. And from there we find the side opposite the acute angle theta. Again, in the right triangle, the side opposite the right angle is the hypotenuse. And the hypotenuse is x. And the side adjacent to the acute angle theta is 7. Adjacent side is 7. And we want to find tangent theta, which is equal to the ratio of the opposite to the adjacent. And what we want is the side opposite theta, which is this side of the right triangle. And we can find this by using the Pythagorean theorem that says the square of the hypotenuse, x squared, is equal to the sum of the squares of the two other sides. The opposite side, which I will denote by y, plus the square of the adjacent side 7. Again, by Pythagorean theorem, the square of the hypotenuse x squared is equal to the sum of the squares of the two other sides, y squared plus 7 squared. And from this equation, we can solve for y transpose 7 squared to the left hand side, we have x squared minus 7 squared, which is 49. Again, 7 squared is 49, transpose to the left, minus 49. And we have y squared at the right hand side, and to get y, we get the square root of both sides. This is originally y squared, and we take the square root of both sides. Therefore, y is equal to the square root of x squared minus 49. Therefore, the tangent of theta is equal to opposite side, which we denote by y, and the value is the square root of x squared minus 49. Over the adjacent side, and the adjacent side is 7. We now rewrite this answer in terms of the variable x. This is now equal to ln of secant theta is x over 7, plus tangent theta. And tangent theta is equal to square root of x squared minus 49 over 7. Plus the constant of integration c. Therefore, the integral of dx over the square root of x squared minus 49 is equal to ln of x plus 7 plus square root of x squared minus 49 over 7 plus c. For our next example, consider the following integral. We have the integral of x squared plus 2. This is an example where we would also use integration by trigonometric substitution. But you might say that how can we use trigonometric substitution when we do not have the radical sign in the given integral? Well, actually, the x squared plus 2 can be written as the square root of the square of quantity x squared plus 2. Again, the binomial x squared plus 2 can be written as the square root of the square of x squared plus 2. So now we have the radical sign in the denominator, and we have the sum of the square of x, and 2 can also be written as a square of the square root of 2. Again, the constant 2 can be written as the square of the square root of 2. If you simplify the square of the square root of 2, it simplifies the 2. So this implies that the constant a in the trigonometric substitution that we will use is equal to the square root of 2. And for this, now this expression is now similar to the square root of x squared plus the square of a constant, for which we let x equals a times tangent theta. Where a is equal to square root of 2. Now we differentiate both sides. Derivative of x with respect to x is 1, multiply it by dx, we get dx. And derivative of square root of 2 times tangent theta is equal to square root of 2 times derivative of tangent theta times derivative of theta is 1 multiplied by d theta. Hence, derivative of square root of 2 times tangent theta equals square root of 2 times secant squared theta. Derivative of tangent theta is secant squared theta. Derivative of theta is 1 multiplied by d theta equals d theta. And in the given integral, we replace dx with square root of 2 secant squared theta d theta. And we replace x with square root of 2 tangent theta. The given integral now is equal to the integral of dx square root of 2 secant squared theta d theta. Divide by the square of x is square root of 2 times tangent theta, square it. Plus 2. And we simplify by taking the square of the square root of 2 times tangent theta. And this expression is equal to integral of square root of 2 secant squared theta d theta. In the denominator, by property of exponent, the square of square root of 2 times tangent theta is equal to the square root of 2 multiplied by the square of tangent theta. And the square root of 2 simplifies to 2 multiplied by square of tangent theta, tangent squared theta. Hence, the square root of 2 tangent theta is equal to 2 times tangent squared theta. And we have a common factor in the denominator, which is 2, and we factor out 2 from the denominator. And this expression is equal to the integral of square root of 2 secant squared theta d theta over 2 times quantity tangent squared theta plus 1. When we factor out the common factor 2, the other factor, tangent squared theta plus 1 is obtained by dividing each of these terms, 2 tangent squared theta and 2 by 2. 2 tangent squared theta divided by 2 is tangent squared theta plus 2 divided by the common factor 2 is 1. And to this tangent squared theta plus 1, we make use of a Pythagorean identity. One of the three Pythagorean identities says that the square of tangent plus 1 is equal to the square of secant theta. So this expression simplifies to square root of 2 secant squared theta d theta over 2 multiplied by tangent squared theta plus 1 is secant squared theta. Hence, the denominator simplifies to 2 times secant squared theta. Since square root of 2 over 2 is a constant, we apply one of the integration rules. We can take square root of 2 over 2 out of the integral sign. And secant squared theta over secant squared theta will cancel out because it's equal to 1. And we are left with integral of d theta. And the integral of d theta is theta plus c, the constant of integration. Again, we have to write this answer back in terms of the original variable x. From this equation, we solve for theta. Tangent theta is equal to x divided by square root of 2. And from this equation, we solve for theta. Theta now is equal to inverse tangent or shift tangent of x over square root of 2. Therefore, this is now equal to square root of 2 over 2. Multiply by theta. Theta is tangent, shift tangent or inverse tangent of x over square root of 2. Plus the constant of integration c. Therefore, the integral of dx over x squared plus 2 is equal to square root of 2 over 2 multiplied by shift tangent or inverse tangent of x over square root of 2 plus c. For your practice, please try the following exercises. Evaluate. Number 1, integral of dx over square root of x squared plus 25. Number 2, integral of dx over square root of x squared minus 36. Number 3, integral of dx over square root of 9 minus x squared. And last, integral of dx over x squared minus 3. The last exercise is similar to our last example, except that we are now given x squared minus 3. And that completes our lesson for today on trigonometric substitution. In the next lesson, we will take more examples for integration by trigonometric substitution. If you have question about the lesson today, you ask your question in the comments below. But don't forget to subscribe to my YouTube channel, Art Kalisan, the channel of learning and leisure. Thank you for joining me in my class today in Integral Calculus.